Hello, this is Dr. William MacLeod from docmctutor.com. Today we're going to talk about simple harmonic motion. So what is simple harmonic motion? Well, simple harmonic motion is an object that is oscillating about an equilibrium position, and there's a restoring force bringing that object back to equilibrium. So the force and therefore the acceleration are proportional to displacement. And I suppose a book definition of it could be when an object is displaced from its equilibrium or rest position and the unbalanced force is proportional to the displacement of the object and acts in the opposite direction, the motion is said to be simple harmonic. Okay, there's the book definition. So it seems a bit dry so far, doesn't it? And you may be wondering, what's the interest in studying simple harmonic motion? Well, in fact, there's very many applications for simple harmonic motion. We've got applications in quantum mechanics. We've got applications, for example, a cord and bungee jumping, oscillating up and down. We've got applications with a guitar string, sort of strumming a guitar string. You've got applications in earthquakes, pendulums, masses on springs. So there's all sorts of applications we can find in the real world roundabout us, both in science and in engineering applications. So let's think about an engineering application first of all. So this is an image there of the Millennium Bridge, and no surprise there, it was opened in the year 2000 in London, and that's why it's the Millennium Bridge of London. So, but it's known as in London as the Wobbly Bridge. Well, why is that? Well, when it first opened up, what happened was, well, it's a pedestrian bridge, and there was many pedestrians going across it, and the bridge started sort of oscillating backwards and forwards. So obviously that wasn't a good idea. So they closed the bridge down, and they put on some more damping systems on it to stop it sort of oscillating in a harmonic way. So that was one, maybe I suppose you'd call that a negative application of simple harmonic motion. Another application, which I've discussed in a video I made a while back on quantum mechanics, more applied to sort of quantum chemistry, where we've got the example there of a hydrogen molecule. So you get a hydrogen molecule which is vibrating backwards and forwards, and that can be described in terms of simple harmonic motion. In fact, that would have applications in the Schrödinger equation and working out the energies for vibrating molecules and the energies in molecules. So that's one application of it in quantum mechanics. Now let's think about Hooke's law. So here I've got it's a rather messy slide. I'm sorry. There on the left-hand side, you've got Hooke's law as applied to a pendulum, and the right-hand side, you've got Hooke's law as applied to a mass on a spring vibrating up and down. So let's look at the pendulum first of all. Well, you can see that the pendulum there has the mass on the pendulum would be pulled down towards the Earth, obviously by the force of gravity. So that was weight is equal to mass times gravity, and the weight can be split up into horizontal and vertical components. Now the horizontal component would be the restoring force for the pendulum, and that would be mg sine theta. So that would be the force part in Hooke's law. So you can sort of do a bit of algebra in Hooke's law using the mg sine theta as the force, and also you can make an approximation, which I won't discuss, but it's actually given in the slide there if you want to look over it. And finally, you can come out with this relationship there, that acceleration of the pendulum is equal to minus g over L, which is the length of the pendulum, times the arc length. So there's one application of Hooke's law for the pendulum. For the spring, what you can say is that mg, the weight, is equal to, or the force is equal to k over x. The force is equal to mg, which is equal to k times x. So the k would be equal to mg divided by x, x being the displacement from the equilibrium position. Okay, so that's Hooke's law for us. Let's look at some other equations for simple harmonic motion. So we've alluded to that equation at the top there. The acceleration is proportional to negative displacement. Okay, and the equation there, y is equal to a sine omega t, where omega is the angular frequency, a is the amplitude, and y is the displacement from the equilibrium position. Simple harmonic motion can be described in terms of sine and cosine waves. So that one there, y is equal to a sine omega t, can be applied when the displacement, that is the y, is equal to 0 when t is equal to 0. So that's when you can apply that equation. And the angular frequency would be omega is equal to 2 pi times the frequency. So if you wanted to work out the velocity, you would differentiate, you would dy over dt, and that would give you a omega cos omega t. If you wanted to work out acceleration, you would differentiate that again. You would do dv over dt, and that gives you finally minus omega squared times y. And that is one of the equations which you use quite a lot in simple harmonic motion. This acceleration is minus omega squared times y. Now let's think about the relationship between the displacement, the velocity, and acceleration for simple harmonic motion. So if you think about at the equilibrium position, so if you've got like a pendulum at equilibrium position, or you've got the spring with a mass on at equilibrium position, equilibrium position, that would mean that the forces are all balanced out. In other words, the resultant force is 0, and if the resultant force is 0, necessarily the acceleration is 0. So there we've got acceleration is 0. The displacement therefore would be 0 because it's equilibrium position, and because it's an equilibrium position, the potential energy is 0, but the kinetic energy is at a maximum, which means the velocity is at a maximum. So like, if acceleration is 0, displacement is at 0, the velocity is at a maximum. Okay, we need to know how to, in advanced higher physics, we need to know how to derive the equation for the maximum velocity for simple harmonic motion. So we've got y is equal to a sine omega t. At maximum velocity, y is equal to 0 when time is equal to 0. Okay. So we do dy over dt, which we've already done, which is in the previous slide, which is amplitude is times angular frequency times cos times angular frequency times time. So if time is 0, that would mean cos 0, because cos 0 is 1, that means we can have velocity is equal to a times angular frequency, that expression there. Velocity is equal to a times angular frequency. And we know from higher maths that sine squared omega t plus cos squared omega t is equal to 1. So we can say that cos squared omega t is equal to 1 minus sine squared omega t. So if we can now say that velocity squared is equal to a squared omega squared 1 minus sine squared times omega t. We get this expression there. So what we can do now is we can now say that velocity is equal to a omega times the square root of 1 minus sine squared omega t. And we can see here we've got the equation that y squared is equal to a squared sine squared omega t at the top there. So we can put that into the expression to get the equation. Velocity is equal to omega times the square root of a squared minus a squared times y squared divided by a squared. And then that simplifies to give us the equation which we use for maximum velocity, which is velocity is equal to, that should be plus or negative, angular frequency, omega, times the square root of a squared minus y squared. So I know I went through that very quickly, but you can sort of like look over the algebra of it, make sure you're convinced about the derivation, and then practice it, because it does sometimes come up in the advanced higher physics papers. So let's now think about kinetic and potential energy as far as simple harmonic motion goes. Well, what can we say about the combination of the kinetic and potential energy? Well, we know that energy is conserved, isn't it? So the combination of kinetic and potential energy would always sort of stay constant, assuming there's no resistance, of course, at the sort of hindering the energy. So what you've got there is you've got a constant energy here on the graph there, and the kinetic and potential energy would be equal. The combination of kinetic and potential would be equal to that total energy. So we can make a few sort of like comments about that. Well, we can say that the kinetic energy plus the half the mass times velocity squared is equal to half the mass times omega times times the square root of a squared y squared, and that's all squared like that. So we'll get that expression here, okay? And that is really just replacing the velocity squared with the equation we had in that slide there. You see the velocity there. So we, instead of the velocity squared, we put in the equation for the maximum velocity for a simple harmonic motion. And that gives us this expression there, half the mass times angular frequency squared times a squared minus y squared. So that would be the maximum kinetic energy of for simple harmonic motion. And maximum kinetic energy would also be equal to the total energy. And the potential energy, how would we work out the potential energy? Well, the maximum potential energy would just be equal to the maximum kinetic energy. But for any variation in between, we can use the relationship that the potential energy is equal to total energy minus the kinetic energy. And there we've got the expression for that at the bottom of the slide there. We've got the potential energy is equal to the total energy minus the kinetic energy. Okay, we mentioned damping and how engineers had to sort out the Millennium Bridge and putting in more damping systems to stop it oscillating. So we'll get three different types of damping there, but we'll just concentrate on two of them. We've got under damping there, where you've got a system where you've got something oscillating, and then you let it the oscillation sort of slow down gradually. So that means the amplitude of the oscillations gets less and less until it stops oscillating. And then you've got critical damping, in which case you stop the oscillating system all of a sudden. You basically stop it oscillating. So that's what this second graph shows. It shows critical damping. So let's summarize what we've just discussed there. Well, simple harmonic motion has many important applications. It's applications in quantum mechanics, it's applications in engineering, all sorts of applications. Simple harmonic motion is an object that oscillates about an equilibrium position, and it has a restoring force bringing it back to the equilibrium position. We looked at Hooke's law, which is F is equal to minus Ky, K being the constant. It's called the spring constant. We're dealing with a spring and a mass on it, and Y is the displacement from the equilibrium position. We also looked at Y is equal to A sine omega t. Y is the displacement from the equilibrium position, A is the amplitude, and omega is angular frequency, and t is the time. So Y is equal to 0 when t is equal to 0, when we're using that relationship there. And angular frequency can be described as 2 pi times the frequency. So the maximum velocity, that happens when the when the object is at its equilibrium position, and we derived an equation for that. So the maximum velocity would be v is equal to plus or minus the angular frequency times the square root of a squared minus y squared. And then we discussed briefly about damping, did we not? Okay, so let's look at some past paper questions. Now, these are past paper questions based on advanced higher physics, the SQA system, but I mean, they'll still be relevant to other exam bodies, such as IB and A-level. So the first question there, it shows a student is investigating simple harmonic motion. So an oscillating mass on the spring and a motion sensor connected to a computer are used in the investigation. This is shown in the figure, so we've got the figure there. The student raises the mass from its real rest position, and then releases it. The computer starts recording data when the mass is released. The student plans to model the displacement y of the mass from its rest position using that expression, y is equal to a sine omega t, where the symbols have their usual meaning. Explain why the student is incorrect. Well, when you're using that equation, that assumes that y is 0 when t is equal to 0. But in this case, he's actually raised the mass from the equilibrium position, so y is not 0. So we can't use that expression. Now, the next question. This is a sort of bit of algebra you have to use here. It's saying the unbalanced force acting on the mass is given by the expression. So you've got the expression there. F is equal to minus m omega squared y. Hooke's law is given by the expression F is equal to minus ky, where k is the spring constant. By comparing these expressions, show that the frequency of the oscillation can be described by the relationship. So you've got the equation there. So what you do is, you do force is equal to minus m omega squared y is equal to minus ky. You rearrange that to get omega squared is equal to my divided by ky. So then you know that omega is equal to the square root of k over m. You also know that the omega, the angular frequency, is 2 pi f, isn't it? So you can combine that with that equation there, and you do a little bit of algebra on it, and you end up with the frequency is equal to 1 over 2 pi multiplied by the square root of k over m. So that's the expression that we were told to find. So we can do it. Okay, the next question, it says there, the student measures the mass to be 0.5 kilograms and the period of oscillation to be 0.8 seconds. Determine a value for the spring constant. So you can use the equation that was given in part B, part 1 there, and what you can do is, determine the value of the spring constant. Yeah, so you just put in your numbers. You've got the frequency is 1 over the period. So the period is 0.8. So you can work out the frequency. So you know the frequency and you know the mass. So you put in all those values into the equation and you end up with K being 31 newtons per meter. Right, so next question. The student plans to repeat the experiment using the same mass and a second spring, which is a spring constant, twice the value of the original. Okay, so you use the equation that was given, and you give the spring, you double the spring constant, 2 times 31, and you end up with the frequency to be 1.77 when you do that. So therefore, to determine the period, it's just period is equal to 1 over frequency. You do 1 over 1.77 and you end up getting 0.56 seconds. Right, the next question there is, you've got 3 different graphs there. It says the student obtained graphs showing the variation of displacement with time, velocity, and acceleration. The student forgets to label the y-axis for each graph, complete the labeling of the y-axis for each graph. So remember that the acceleration would be 0 when the displacement is 0, isn't it? And so what we've got there is, you can see in the top graph there, the acceleration is 0. When the second graph must be the displacement, because the displacement is 0 at the same part that the acceleration is 0. And you also know that the velocity, you can also see that the velocity is at a maximum, in fact, when the acceleration is 0. So in other words, the top one would be acceleration, the middle one would be displacement, and the bottom one would be velocity. Okay, so next question there. We've got a ball bearing is released from height h on a smooth curved track as shown in figure 9a. The ball bearing oscillates in the track about position P. The motion of the ball bearing can be modelled as simple harmonic motion. The ball bearing makes 1.5 oscillations in 2.5 seconds. Show that the angular frequency of the ball bearing is 3.8 radians per second. Well, you use the relationship, the angular frequency is equal to 2 pi times the frequency. So the frequency would be, well, it's 1.5 oscillations in 2.5 seconds. So the frequency is just 1.5 divided by 2.5. So we can put that together to give you 2 pi times 1.5 divided by 2.5, and that indeed does give you 3.8 radians per second. Right, the next question, it says the horizontal displacement x of the ball bearing from position P at a time t can be predicted using that relationship there. Using calculus methods, show that this relationship is consistent with simple harmonic motion. Well, we do a dx over dt, so we differentiate it, and we end up getting minus 3.8, and then times in the brackets minus 0.2 sine 3.8 times t. Okay, then if you differentiate it again, you'll end up getting acceleration. So that would be minus 3.8 squared, and then you've got in the brackets minus 0.2 cos 3.8 times t. So that is in the form of acceleration is equal to minus the angular frequency squared times x, or the displacement. So that would be consistent, isn't it, with simple harmonic motion, because it fits in with that relationship for acceleration for simple harmonic motion. Okay, let's look at the next question. Determine the maximum speed of the ball bearing during its motion. Well, there we use the maximum velocity equation. We know that the angular frequency is 3.8. The amplitude is the amplitude would be 0.2. We can see that from the equation, can't we? This the equation that x is equal to 0.2 cos 3.8 t. So that means that the amplitude would be 0.2, and the maximum velocity, the displacement is 0, so the y would be 0. So you plug in all those numbers and you end up getting 0.76 meters per second. Next question, determine the height from which the ball bearing was released. Space for the working and answers. Okay, so you know the maximum velocity, and therefore you can work out the maximum kinetic energy, which would also be the maximum potential energy. And from the maximum potential energy, you can work out the height. So that's what's really worked out there in that question there, isn't it? So, and then you end up getting the height being 2.9 times 10 to the -2 meters. Okay, next question. In practice, the maximum horizontal displacement of the ball bearing decreases with time. A graph showing the variation of horizontal displacement of the ball bearing from position P with time is shown. So you've got it there. Sketch a graph showing how the vertical displacement of the ball bearing from position P changes over the same time period. Numerical values are not required. So what you've got there is you would have it sort of the amplitude decreasing as well, wouldn't you? In a similar fashion. So it's finally, the amplitude is getting less and less. Okay, a home improvement shop has a machine that can produce paint of any colour. Small amounts of pigment are added to paint in a tin. The tin is then shaken to produce a uniform colour. The tin is placed in the machine and clamped securely. During shaking, the oscillation of the tin in the vertical plane can be modelled as a simple harmonic motion. Tin of paint has a mass of 3.67 kilograms. The tin is shaken at 580 oscillations per minute, and the amplitude of the motion is 0.013 meters. Show that the angular frequency of the tin is 61 radians per second. So use your angular frequency equation, 2 pi f. So you've got the frequency being 580, because 580 oscillations, divided by 60 seconds. So that gives you 61 radians per second, which does, you have shown that the angular frequency then is 61 radians per second. Calculate the maximum kinetic energy. Well, that maximum kinetic energy would be, you would use this equation there. You've got half the mass times angular frequency squared times the a squared minus the y squared. So at the maximum kinetic energy, the y would be 0, wouldn't it? So that means that the maximum kinetic energy is 1.2 joules, which is also the maximum energy. Right, pushing on. There you've, on the axis below, sketch a graph showing the variations of the kinetic energy of the tin with the vertical displacement from the equilibrium position. So in that one there, you know that the oscillation, the amplitude is 0.13 meters. So you've got negative 0.13 and negative 0.13 is the displacement. And each, when it gets to the maximum displacement, the kinetic energy is at a minimum, potential energy is at a maximum. So you actually draw the graph, and we've shown it there, with the minimum kinetic energies at 0.013 either side of the equilibrium position. State the magnitude and direction of the acceleration of the tin when the coin just loses contact with the lid. So this is on about a coin that hits the lid and it loses contact with it. Well, the acceleration would be gravity, 9.8 meters per second going down. And the next question it's asking there, to determine the magnitude of the displacement of the tin from its equilibrium position when the coin just loses contact with the lid. So use the expression acceleration is equal to minus the angular frequency squared times y, the displacement. So you're trying to find out y, the displacement. So you put in the acceleration, 9.8. You know the angular frequency is 61. So that you work out the y is equal to 2.6 times 10 to the minus 3 meters. Okay, well that's us finished for simple harmonic motion. Hopefully this video was of some use to you.